In this video, I'm going to explain a little bit about our weak acid titration lab that we're doing in class this week. I'm not going to go into a whole lot of detail about the theory and the background information behind it because the lab manual actually does a really good job of kind of walking through everything in a more granular way. And by the way, I'm not taking credit for the lab manual. Dr. Carricker wrote that. We're just using the lab that he wrote. In this video, I am going to show you some visuals to go along with the explanation because I think that'll be really helpful as you get ready to actually do the titration this week. And we'll use HA to represent that acid because each group is going to have a different weak acid that they're using. So we'll just use the general HA. You'll be titrating that with NaOH, sodium hydroxide, and it's going to produce the ionic salt out of that, so the sodium cation, and then our conjugate base, this A-, which again will depend on what weak acid you're using. And it'll also make water, the hydrogen and the hydroxide. Now, by this point, we've done a couple of titrations already. You did the strong acid, strong base titration in 10th grade, and then, of course, we did a redox titration back in semester 1. And so you might recall that generally the goal of a titration procedure is to calculate the molarity of some analyte. So, for example, usually in a titration, we're trying to calculate the molarity of the acid. That's the analyte that we're titrating into. That is not the case for this week's lab. This time around, our goal for this titration procedure is to determine the identity of our unknown weak acid. So I mentioned that each group is going to get a different weak acid, and you're not going to know what it is. It's just going to be acid A, B, C, D, etc. And you're going to do your analysis to figure out what weak acid you have. So this titration, not anything about concentration this time, all about determining what the unknown is. So what I'm going to do over the next couple of minutes is explain a little bit about how you're going to do that, and again, kind of show you some visual from the lab procedure that I did to kind of help you get ready for the analysis that you're doing this week. So first, let's do a little comparison between the strong acid, strong base titration that you did in 10th grade. So in the strong acid, strong base titration, we titrate to a point that's called equivalence point. And equivalence point exists for all titration procedures. The equivalence point is where moles of acid equal moles of base. Let me write that down. So in a strong acid, strong base titration, at the equivalence point, pH is equal to 7. And that's also an idea that we talked about when we were talking about acid-base theory in class, that pH will be 7 once you get a full neutralization because you're only making water and then some conjugate base solution of a conjugate base that's not very strong, right? The conjugate bases of strong acids are really not good conjugate bases. So pH is 7. And so for that strong acid, strong base titration, we would use the acid-based indicator phenolphthalein. Let me see if I can spell that. Phenol, and it's Pthalein. Phenolphthalein. Phenolphthalein changes color. It goes from clear to this like really bright pink purple color, like the pen that I'm using, at a pH of about... It's like 8.3 or 8.4. So a slightly basic pH. And so we use that to identify when we've fully neutralized, right? Because just a little bit of excess strong base will push the pH up and make the phenolphthalein change color. So it doesn't change color right at 7, but it changes color close enough for our analysis. Now in a weak acid strong base titration, which is what we're doing in lab this week, pH at equivalence is going to be greater than 7. And the reason for that is because a weak acid makes a conjugate base of significant strength, right? The conjugate bases of weak acids have non-negligible strength. And so you're going to end up with a basic solution because you're making that conjugate base. So you're neutralizing all the acid, but you're making a conjugate base as well. And that conjugate base is going to push the pH above 7. And so when we say greater than 7, I mean, it'll depend on the weak acid that you use, but we're expecting, pH at equivalence to be probably around 10, maybe a little bit more. Again, it'll depend on the weak acid. So that makes that, or that means that phenolphthalein is not suitable for our indicator here, right? Because phenolphthalein is going to change color too quickly, like too soon before we reach the equivalence point. How are we going to know that we're at equivalence? Well, this time around, we're not actually going to use an acid-base indicator. Instead, we're going to use a pH meter. So we're going to use a pH meter that connects to our laptops with the vernier interface. And we're actually going to collect numerical pH data as part of our analysis this time. So if you don't already have the Logger, it's called Logger Lite software downloaded on your laptop, there should be a download link on MyCrystal, so you can put that on your laptop. That is approved by the school. It's a really light, not intensive software, so it should run fine on any laptop, but you're going to need that to collect your data. So let's look at some of the data we're going to collect, as well as sort of the setup, and again, I'll explain a little bit more about the analysis. Okay, so here's a little video of the pH meter and my lab setup. So you can see that we have a magnetic stir bar in our reaction flask. You can see it stirring there. It sits on top of the hot plate, and hot plate's not on applying heat, but it's just applying the stir function. And then the pH meter is just sitting in the solution. And for my trial, I just had the pH meter kind of leaning in there. We can get a clamp and kind of clean that up a little bit and make it like a little bit nicer, but there's an optical sensor at the very end of the pH meter that just needs to be in the solution. And as long as it's stirring, it'll be fine. And then you can see the tip of the burette here where we're actually titrating. Okay, so that's what our lab setup is going to look like. So not terribly intensive, but again, quite a bit different than some of the titration stuff we've done before. All right, so what about the data that you're going to collect for this lab? Well, you can see from this picture that I took of my computer, this is what the data and graph is going to look like for this lab. This is what we call a titration curve. So you can see over here on the table on the left, I put in the volume of NaOH that's being dispensed. This is the total volume, so I went 1 milliliter at a time, and then it records the pH, and you can see the current pH reading there at the bottom left, 12.47. And so we get all these data points, and it makes a curve for us, and so your curve will look something like this. Now, where you get the kind of steep increase over here, this is the equivalence point. Equivalence point. Right, this is where moles of acid equal moles of base. It's about halfway up the steep portion of the curve over here on the far right. But in a weak acid strong base titration, we're actually not concerned about the equivalence point itself. We're concerned about what's called halfway to equivalence. And halfway to equivalence, we mean half the volume it took to get to the equivalence point. Now, the way the software works is if you mouse over this red line, it will show you what data points, it'll highlight them in the table. But for our purposes, let's say that equivalence point is, we'll call it 58 milliliters, right? So after we added 58 milliliters of NaOH, we reached the equivalence point. So that means that halfway to equivalence point is 29 milliliters. So here's 30. It's marked on the graph. So 29 is right below that. So we'll call it there, 29 milliliters. And this is halfway to equivalence. And the reason that halfway to equivalence is so important is because at halfway to equivalence, the pH equals the pKa for the weak acid. So at halfway to equivalence, pH equals pKa for your weak acid. And pKa is a really good way to identify what weak acid you've got. right? We can figure out which weak acid we're looking at by comparing pKa values. Now, again, the lab manual kind of shows the math behind this, shows the proof behind this, but that's the general idea, is that halfway to equivalence, pH equals pKa. Okay, so you might say, well, what if we have two weak acids that have similar pKa's or similar Ka values? Well, the other way that we're going to verify the weak acid that we're looking at is we're also going to calculate its molar mass. And its molar mass also comes from this volume of NaOH at equivalence. So we've got to calculate the moles of NaOH. So I'll do that with my data here. So this is rearrangement of the moles over liters equation. So moles is going to be molar, big M. My NaOH was a 0.2 molar solution. Yours might vary slightly because you're going to make your own. Times the volume at the equivalence point, 0.058 liters is what we're using here. Okay, that gives us the moles of NaOH. And we know that at equivalence point, moles of acid equals moles of base. So we know that there must also be this many moles of weak acid in this solution, right, at the equivalence point, or because that's the equivalence point. And so to calculate molar mass, and I feel like this is a calculation we've done a few times. I had one on the test review. I know we did one on the very first test of the year, right? The units for molar mass are grams per moles. And I just calculated my moles, right, 0.0116. And then the grams value, what goes in the top here, is going to be the mass that you used to prep your acid solution. And I think for mine, it was like 0.503 or something like that, that many grams. And so if I just do grams over moles, then that will give me the molar mass, and that gives me another way to verify the weak acid that I've got. Okay. So this is a lab that we're going to try to get it done in one trial. Like one really good trial can give us the results that we need. Of course, we can do it again if it comes out inconclusive. But this should be a fun one. If you haven't already, definitely go read the lab manual. Again, there's a lot of really good information in there that Dr. Carricker wrote into that thing. So that's also going to be really helpful before you come to the lab this week. But I hope this also provided some context and a good visual. All right, I'll see you soon.